Right. Hi, everyone. So today we're very happy to have Sam from Princeton, formerly at MIT, give us a talk about subalgebra, subregion duality. Please ask questions. We try to keep the talks very interactive. And please, thanks so much for accepting the talk. Please, Sam.
Yeah, thanks, Neumann, and thanks for the invitation to give a talk. Yeah, so the talk title, I guess, is subalgebra, subregion duality, which is about the emergence of space and time in the ADS-CFT duality. And so yeah, and this is all based on work with Hong Lu at MIT that appeared in these two papers last year. And then mostly what I'll talk about today actually is something that will appear in upcoming work that hopefully will come out soon. So first, to start at a very a basic level, let's make sure that runs. There we go. To start at a very basic level, so what is the ADS-CFT correspondence? So we'll be studying aspects of this correspondence, so we should define what it is. And so, very, very roughly what it says is that quantum gravity in some space-time that's asymptotically ADS, where ADS is anti-de Sitter, a particular solution to Einstein's equation with a negative cosmological constant. Well, that quantum gravity theory should be equivalent to a CFT, a conformal field theory, that we can think of as living on its boundary. And so I've sort of shown this schematically here. If we have this green disk where we have some quantum gravity modes propagating in d+1 dimensions, then ADS-CFT duality tells us that we should be able to describe that quantum gravity theory in terms of a conformal field theory only on this black circle that's its boundary in d dimensions. And so this has been studied for many years, and a lot is known about it. But it's produced a lot of interesting results. And so we might wonder, why is that? So one reason is that it's a concrete realization of this holographic principle, the idea that systems with gravity can be described by less degrees of freedom than you would naively think. So instead of needing a full volume's worth of degrees of freedom to describe this gravity system, we can describe it from its boundary, which scales like the area. And the reason that I think one of the reasons it's been so successful is it allows us to treat gravity as an emergent quantum mechanical phenomenon. So we can study this conformal field theory, which is some quantum mechanical system that in principle we understand, and we can study that conformal field theory without having to put in gravity. And this this still lets us learn some things about quantum gravity. So that's sort of the general idea of the ADS-CFT correspondence. And so at the highest level, we have that this bulk gravity theory is dual to some boundary CFT. And in principle, what this means is that if I have my quantum theory of gravity, it has some states. And for each one of those states, there's a corresponding CFT state, and the other way around. So we have a one-to-one correspondence between quantum gravity states and conformal field theory states. And so a simple example of this was discussed by Maldacena in 2001, is the idea that some quantum gravity state that has some low energy description in terms of this eternal ADS black hole, that state should be dual to a pair of conformal field theories in the thermofield double states, some particular entangled state between the two conformal field theories. And so there's parts of this diagram that we understand very well and that have been understood for many years. And so one of those is, for example, is this time-like killing vector outside the horizon. That field we can understand as being dual to this time in the conformal field theory, and formally it goes up on the right and down on the left. And so this has been well understood for some time, and it really lets us understand the exterior regions of this ADS black hole very well. But of course, there's a lot more going on in this picture on the left than in the picture on the right. In particular, we have these horizons, where the time ends, it goes to minus infinity on the past horizon and plus infinity on the future horizon. And it has these interior regions that don't seem to have any direct mapping to the conformal field theory. And there's also notions of infalling observers who fall from an exterior region into the interior. And so there's all these features in the gravity side of the duality that are just not obvious from this picture in the conformal field theory. So coming back to the idea of the ADS-CFT correspondence, in the picture that I just drew for you, we had on the left side that gravity description in terms of a classical space-time, and through the standard parameter mapping in the ADS-CFT correspondence, that kind of space-time is obtained in the limit where g Newton, the gravitational coupling, is going to 0, and that corresponds to many degrees of freedom in the boundary CFT. So to really get that emergent classical geometry picture that we have, we need to be considering something like an n equals infinity CFT. For most of this talk, we're going to try to understand what exactly is meant by this n equals infinity CFT. And in particular, we're going to be interested in these geometric notions that we have in the bulk. So for example, we have space-time subregions in the bulk. We'd like to understand, how do we understand those in the CFT? There's event horizons in the bulk. How do we understand those in the CFT? And similarly, those infalling times. So all of these geometric features of that semi-classical bulk picture, we want to understand how they're described from the boundary perspective, and in particular, because these geometric notions are only sharply defined in this g Newton goes to 0 limit, where the geometry can be treated as approximately classical. That means we're going to have to study objects over here that are defined in this n goes to infinity limit. And so in general, we'd like to understand all of these things. For today's talk, I'm just going to focus on space-time subregions. Great. And so sort of the main takeaway of the talk is related to the emergence of bulk space-time. So what the question we're going to try to answer is, what is the precise mathematical structure in the CFT that describes these bulk geometric objects? And our answer to that question is that the bulk space-time is a geometrization of emergent type 3.1 algebras on the boundary. So what we'll see is that in this large n limit, these type 3.1 algebras emerge rather ubiquitously all over the place. And the space-time is sort of a convenient way of, the bulk space-time is a convenient way of understanding the relationships between those type 3.1 algebras. So these geometric notions in the bulk are related to the properties of those emergent type 3.1 algebras in the boundary theory. Great. So that's it for the motivation. So I'll just stop for a couple of questions in case there's for a couple of seconds in case there's any questions. Great. So now here's just sort of a quick outline of the talk. So first, I'll just review some well-known facts about local algebras in quantum mechanics and in quantum field theory, just to get us all on the same page, and what is the significance of these type 3.1 von Neumann algebras. Then I'll talk in a bit more detail about how we take the large n limit and construct a Hilbert space that's going to describe the bulk effective field theory. And then I'll get to sort of the meat of the talk, this subalgebra subregion duality. I'll talk about how we formulate that and how it's connected to older ideas about bulk subregions, in particular subregion-subregion duality. And then I'll talk about how the subalgebra subregion duality lets us study some more general cases. And then I'll conclude with some discussion of the things I think we can learn from this construction.
Sorry, quick question, Sam.
Yeah.
Are you going to comment on SYK and whether there exists type 3.1 algebra emerging in SYK in the large n limit or not?
That I won't comment on. Yeah.
So you do not is it understood whether there is a type 3 1 algebra emerging SYK?
I don't think it's understood in complete detail. I think that's a very natural place to look for this, because it's a very simple setting, and the bulk picture tells us that it should be emergent. That you should have this emergent algebra, but it's not something I've studied in detail. It's something I'd like to look at more.
Okay, thank you.
Yeah, great, thanks. Great. Okay, so let's talk about the idea of local algebras in quantum mechanics. So in quantum mechanics, if we want to talk about the local algebras, we want to talk about the operators that, somebody who's restricted to a subset of the degrees of freedom, the operators that they can manipulate. So, the sort of simplest setting for this is that we have a bipartite quantum system that has, two sides, a left and a right side. And then acting on those left and right sides are these local operator algebras, the bounded operators on this Hilbert space and the bounded operators on this Hilbert space. And so that's sort of the story of local algebras in quantum mechanics. And there's a nice story about entanglement that we can tell in quantum mechanics that's sort of related to this local algebra structure. So in particular, if we take some global states in this tensor product Hilbert space, then we can compute partial traces to get some reduced density matrices that are just elements of these local algebras. And we can go further and define this von Neumann entropy, which is just some functional of that state. And this might tell us something about the entanglement. And then in this setting, if we have a very highly entangled state, then these row left and row right can both be full rank. And it's only in this case that we can define this modular flow. And so what is modular flow? It's just this automorphism of the algebra that looks like this, some sort of unitary rotation of the algebra, where delta is this modular operator given by this in this particular setting. Great. And so that's the story in quantum mechanics. And then we might wonder if we can tell the same story in relativistic quantum field theory. So, what I've drawn here is just some Rindler decomposition of Minkowski space. And so, if we look at the t equals 0 slice of this spacetime, it goes through the left and the right region. And so we might wonder, can we describe this system in the same way as in quantum mechanics, where we have some Hilbert space for the left degrees of freedom to act on and some Hilbert space for the right degrees of freedom to act on. But it turns out that in relativistic QFT, those Hilbert spaces just don't exist. This H left and H right don't exist. We don't have these Hilbert spaces for the local fields to act on. Similarly, there's not reduced density matrices for those regions. And there's no finite, well-defined entanglement entropy for either of those regions. But that this modular flow, that the modular operator and the corresponding modular flow still exist in that case. And we can think of this, the fact that we don't get many of these familiar quantum mechanical concepts, but we still have modular flow, as reflecting the fact that all states in the Hilbert space are highly entangled. And there's a more fundamental description of this phenomenon, which is that there's a difference between the local operator algebras in quantum mechanics and those in relativistic quantum field theory. And this is very neatly summarized by a classification of von Neumann algebras, because von Neumann algebras have been classified and studied a lot in the math literature. And so in quantum mechanics, we would say that those local algebras are what's called a type 1 von Neumann algebra, whereas in relativistic quantum field theory, they're of type 3-1. And so it's not super important what those types mean, but we have these different types in the two settings, and this sort of can explain a lot of the differences between quantum mechanics and quantum field theory, especially with respect to these local operator algebras. Great. So now let's see how we can apply these ideas of local operator algebras to this particular case that we're interested in, which is the large N limit of some CFT. So if we consider a CFT that has these n by n matrix degrees of freedom, So for example, you could consider something like n equals 4, Super-Yang-Mills theory with gauge group SUN. Then this is some CFT. It has some degrees of freedom that are matrix-like. They might be large, but they're still finite matrices. And in particular, when n is finite, there's just some well-defined Hilbert space. That's the Hilbert space on which the CFT operators act. And if we take the full algebra of operators, on the entire, Hilbert space, it means we need to take the operators on a full Cauchy slice of the CFT. Then that algebra of operators is of type 1. But what can happen is when we try to take the large n limit and understand the large n limit of the CFT, some states and operators that were well defined in the finite n CFT may not survive that large n limit. And this can lead to dramatic changes in the structure of the Hilbert space and of the operator algebras that we get in the large n limit.
Sorry, can I ask a quick question?
Yeah.
So the thing that was never clear to me is that, well, this is the second statement you say is, do you have in mind finite volume quantum field theory? Do you have in mind infinite volume quantum field theory?
Right. That's a good point. I guess. Yeah. I think so. I guess I think maybe it's best to have in mind the finite volume quantum field theory, and then you don't have these IR issues.
Yeah. Okay. Because
Yeah.
I mean, it's probably true for flat space quantum field theory as well, but I've never seen a very clear argument or proof. Maybe I'm just missing something, but yeah.
No. Yeah. That's true. It is trickier in that case because of the IR issues.
Okay.
So I think, yeah, the surprising thing is that even for the finite volume quantum field theory, you get these strange algebraic changes,
Right.
where you maybe have some more control. Yeah.
Thank you.
Great. Okay. So how do we take the large n limit? So I'll just consider this very concrete case that I mentioned before of this n equals 4 Super-Yang-Mills theory. And in that case, we know exactly what are the operators that have a well-defined large n limit. Those are these single trace operators. So where with our operators we can write, as some polynomial of the matrix degrees of freedom, and then in the end, we only take one trace over the matrix indices. And those are the single trace operators, and we can take products of them. And in the finite n theory, if we take all of the products of those, we get back the full CFT algebra. But in the large n limit, then they form a different algebra that has different structures, and I'll call this single trace algebra A. And in particular, if we take this algebra A and we act it on some state psi, we can build a GNS Hilbert space of small excitations around psi. So this is a well-known construction in algebraic quantum field theory due to Gelfand, Neymark, and Siegel, where if we have some algebra and a state on that algebra, we can build those excitations form the structure of a Hilbert space, and we can construct that Hilbert space.
Sorry, Sam?
Yes. Yeah.
Do you mean that the algebra is generated by single trace operators?
Right. So this right. So at finite n, the single trace operators generate the full algebra. And so in this case, what we have to do is consider the products of single trace operators, but we have to restrict the number of operators in that product to not scale with n.
That's right. No, I understood correctly, but yeah, okay, good. Yeah.
Okay, great. Yeah. Right. And so so when we take that algebra in the large n limit, that procedure does close into an algebra. And when we act that on the states, we get this GNS Hilbert space. And this GNS Hilbert space has a special state that I'll call the GNS vacuum state. And this is just a particular state that reproduces the correlation functions of those single trace operators in this original state psi that we started with.
Sorry, I don't mean to be nitpicky. I'm just
Okay.
this an issue I've always been confused about. So the subalgebra exists only in the strict n going to infinity limit, right?
Yes, yes.
But the moment we talk about large n but finite, there is perhaps a notion of approximate subalgebra. Is that
right? I think that's the right idea. I think you can't. I think if you talk about large but finite n, I think you can't get a genuine subalgebra because, of course, if you take enough, if you allow these infinite products, then you'll have some products that are large, that are larger than n.
okay?
In that case.
Yeah. Okay. So we're on the same page. Good. Thank you.
Yes. Yeah. Great. Yeah. But yeah, it would be very interesting if there is some approximate notion that you can define, but I think it wouldn't be a closed algebra. Yeah. Great. And so this GNS Hilbert space, it furnishes a representation of this single trace algebra, and I'll denote this representation by m sub psi. So that's just the representation of these single trace operators on the GNS Hilbert space. Great. And so there's a very analogous sort of bulk story that we can tell alongside this. So in the G goes to 0 limit, then we expect that whatever this quantum gravity theory is and this quantum gravity state, it can be described by some classical solution that I'll just denote here by chi sub psi. And if we quantize perturbations of bulk fields around that solution with some, and acting on some appropriate vacuum states, then we can build, the Fock space of these small bulk excitations around that classical solution. And so one important thing that I'll point out is that this construction depends very much on the state psi, and in particular on its semi-classical description. Once we build this Fock space, we can then talk about the algebra of bulk field perturbations. So these algebras of bulk operators around this classical solution, and that's just this algebra of operators on this Fock space. And I'll denote that by m tilde. And so now we have these two different descriptions of these sort of small excitations around some quantum gravity state, or which should be dual to some CFT state. So what does ADS CFT duality tell us about this? So in particular, this sort of Gn goes to 0 limit, or the n goes to infinity limit of the ADS CFT duality tells us that we should identify this GNS Hilbert space with the Fock space of small excitations in the bulk, and we should identify this GNS vacuum with the vacuum of the Fock space in the bulk. And in particular, we then need to identify this representation of single trace operators on the GNS Hilbert space with those operators, those bounded operators acting on the Fock space in the bulk. And so this is a very familiar statement. This is just a statement of global reconstruction in ADS CFT. But this statement has some interesting implications, because the fact that we can make this identification here, it implies that there must also be an identification of subalgebras. If we have some subalgebra of m psi, it should be possible to interpret that also as a subalgebra of m tilde psi, and therefore some sort of bulk subalgebra. So I'll just sort of give our favorite example of this story, which is in the thermal field double case. So in this case, we actually had two copies of the CFT. So we sort of have a left and right copy of these single trace operators. And our state is this thermal field double state, which is just this entangled state between the left and the right sides. And what we find is that there are sort of two possibilities for the structure of these A left and A right single trace algebras, depending on the temperature of this state psi. So if we're below the Hawking page transition, if we have a low temperature, then these representations of single trace operators should be type 1 von Neumann algebras. And what this means in the bulk is that what we're describing is sort of two copies of global ADS whose excitations, whose small excitations happen to be entangled in some thermal field double state. But in the case that we're above the Hawking page temperature, these representations of single trace operators should be of type 3.1. And that's when we end up with this dual picture that looks like the eternal ADS black hole, where now these left single trace operators are describing a left exterior, and the right single trace operators are describing some right exterior. So that's the general picture of the duality in this algebraic language. And so before I go into more detail, I need to say a little bit more about these single trace operators at large n. So we can imagine a single trace operator that looks like this. The trace of the square of the field strength in Super-Yang-Mills theory, for example. And at finite n, we can express this operator in the following way. The operator satisfies some Heisenberg equations of motion. And so if we consider this operator v of t, we can get that operator from the same operator at t equals 0 by conjugating, with this unitary e to the iht. And in particular, we could expand out this expression for v of t in terms of some coefficients that will depend on time and some complete set of operators on the t equals 0 slice. But importantly, when we write out this expression here on the right-hand side, this complete set of operators OI includes multi-trace CFT operators. So these are operators that will not survive the large n limit. Their correlation functions will be divergent in that limit, and they don't remain in the large n theory. And so in particular, what happens is that as n goes to infinity, we can still define the single trace operator v of t through its correlation functions, but we can no longer express it in terms of some Hamiltonian evolution or in terms of some operators on a single time slice. And this is reflecting the fact that in this large n limit, the single trace operator algebra is described by a generalized free field theory. And so here we have to mention a couple of peculiarities that are related to the fact that we don't have this Hamiltonian evolution anymore in the large n limit, that are sort of well-known properties of generalized free fields. So what I've drawn here is some causal diamond of some region that we can imagine as a subregion on the boundary. And it has two Cauchy slices, this blue slice here and this red slice. And so usually in quantum field theory, we have some hyperbolic equation of motion that allows us to express all the operators here on this slice A2 in terms of operators on A1 and vice versa. And this means that those algebras are the same. But for generalized free fields, this is actually not the case. We no longer have this equation of motion amongst the generalized free fields themselves. And that means that these algebras can actually be different. And so in particular, what this means is that there's a sense in which when we take this large n limit of the CFT and we end up with these generalized free fields that don't obey the equation of motion, there are many more type 3.1 subalgebras, because we now have distinct subalgebras for different space-time subregions, rather than just having distinct subalgebras for causally complete subregions. So we have these additional type 3.1 subalgebras emerging in the boundary theory, and on the gravity side, we expect that if we consider the bulk fields localized to some causally complete subregion, we should obtain some type 3.1 subalgebra to describing those bulk fields restricted to that subregion. And so the proposal of subalgebra subregion duality is very simple. It's just that the algebra of local bulk operators in any causally complete bulk subregion that I'll denote by B is dual to some emergent type 3.1 subalgebra in the large N limit of the CFT. So we have all of these additional emergent type 3.1 subalgebras in the large N limit of the CFT, and they should be describing the algebras of bulk fields restricted to particular subregions in the bulk. So in particular, if we have some algebra algebra of bulk fields restricted to this subregion B, then there should be in the large N limit of the CFT some subalgebra that is exactly equal to that. And so in particular, this generalizes the RT surface formulation of subregion-subregion duality, where for certain bulk subregions, we can describe some sort of boundary dual for certain bulk subregions, but not for generic bulk subregions. And so I'll come back to that in a little bit. And so first, I'll go into a bit more detail about our proposal, and how exactly do we assign these algebras to subregions. So if we think of some boundary spatial subregion R, there are sort of two natural subalgebras to associate with that subregion in the large N limit. And so I'll just explain this notation a bit here. So one subalgebra that we could associate is what I'll denote by M sub R hat, which for convenience I'll define to be equal to this Y sub R hat. So if we take this subregion R, that's some spatial subregion on the boundary, by R hat, I just mean take its causal completion. So for example, if R was some interval on the boundary, then R hat would be the causal diamond of that interval. And in this construction here on the right, what this means is that we take the full algebra of single trace operators on the boundary, we take the large N limits, and we get that M sub psi that I mentioned before, this representation of single trace algebras, of single trace operators. And then we restrict that algebra, which is now just the restriction of some generalized free field algebra, to the subregion R hat, this spacetime subregion, boundary spacetime subregion. And then we would take its double commutant to get a von Neumann algebra. And so this sort of gives a natural subalgebra to associate to the subregion R. But there's another procedure that we could have done to understand to assign a subalgebra to the subregion R. And what that is that we first take by B, this denotes the full CFT algebra that exists in at finite n. We can take that full CFT algebra, restrict it to operators supported in some subregion, and then take the limit as n goes to infinity, keeping only operators whose correlation functions, only operators in this subalgebra, whose correlation functions in psi are well defined in the large N limit. And that gives another natural subalgebra to assign to this subregion R in the large N limit. And by definition, this algebra X sub R contains this algebra Y sub R, but in general, this will not be equal. And in particular, we propose that X sub R is dual to the entanglement wedge, while Y sub R hat is dual to the causal wedge associated to those regions. So, this sort of potential for a proper inclusion can give an algebraic understanding of cases where the entanglement wedge exceeds the causal wedge, and we'll talk in a few slides about an explicit example of that. Great. So let me just describe the properties of these two sort of different types of large N algebras. First, sort of as I mentioned, so by definition, this algebra that we assign to R through this X procedure, that in that procedure it was defined to be the limit of some CFT algebra restricted to that subregion. And so in particular, at all finite n, we had the equation of motion. And so this X sub R algebra is actually equal to the algebra that we would assign to its causal completion. but this is actually not in general true for the generalized free fields procedure, where we first go to n equals infinity and then consider restricting to a subregion. Assuming that your CFT algebras obeyed what's called Hogg duality at finite n, this X algebra, these X algebras should obey Hogg duality in that limit. So that in particular, this means that the algebra associated to the causal complement of some region is equal to the commutants of the algebra associated to that region. And generically, what happens is that this is actually violated for generalized free fields, for these for the algebras constructed by first taking the generalized free field and then restricting to a subregion. And so another natural property that we might ask about is something called additivity, which looks like this. And so we ask if we have some sort of composite subregion that's built out of two parts that I'll denote by R and S. Is that algebra equal to the algebra generated by R and S separately? And what we find is that generically this sort of X procedure of getting the subregion algebra violates this additivity, whereas on the Y side, where we take the generalized free field and restrict to a subregion, essentially by definition, this satisfies sort of a modified version of additivity. So one thing is usually when one talks about additivity in quantum field theory, you need to do a causal completion on this side, because one in general only assigns algebras to causally complete subregions. But for generalized free fields, as I mentioned, there's no equation of motion, and so there's sort of it's possible to assign these subalgebras to non-causally complete subregions.
Sorry, quick question, Sam.
Yes, yeah.
If I take the say a vacuum ADS or some sort of like fine temperature ADS, and then I'm going to look at the Poincare patch, let's say the vacuum ADS. On the boundary, I can define both of these algebras, right? Then what is the distinction between the two exactly? Yeah, like in the bulk, how would you interpret this? So in the case of a subregion, you were saying one of them has to do with the entanglement wedge, the other one has to do with a causal wedge.
Right.
But if I just take a full Poincare patch,
right.
I still have an algebra inclusion, but yeah, how do I interpret the bulk? How does it connect to the bulk?
Right. So yeah. So in that case, I guess right. So if I take the full if I take sort of the full boundary spacetime, then these two algebras should coincide.
It's not that's the thing that's unclear to me, because your principle of under time evolution, you generate all sorts of higher point multi-trace operators, right? Order n trace operators seems to apply in that case as well.
Right. So do you mean under global time evolution, not Poincare time?
No, well, no, I should talk about Poincare time evolution.
Right. Okay. So under right. Sorry. Yeah. So in that case, yeah. Right. So yeah. I guess maybe the thing is that when I talk about the and hope maybe this gets at your point, but let me know if it doesn't. Yeah, so in that case, the causal completion of the region R would be sort of a whole Cauchy slice of the boundary, and the causal completion will be the entire boundary spacetime. And so in that case, the bulk dual is, I think in each case is the entire Poincare patch.
The reason I said this is that in the analogy, in the discussion that you have, I understand that you have a subregion on the boundary in mind. And what you end up getting is an inclusion of a type 3-1 algebra inside another type 2-1 algebra, right? One of the types.
Right, yeah, for subregions, yes.
Right. So now I was wondering whether if you do take the limit of decompactifying the subregion, you do end up with an inclusion of a type 3-1 inside type 1, which I think would be very interesting. But anyway, maybe
Right.
we'll discuss this. It is a singular limit. I understand it's a singular limit of this.
Right, yeah, that would be interesting to consider that limit. Yeah.
Okay, thanks.
Right, yeah. There's that'd be great to discuss after. There's some subtleties that happen that it seems as though, sort of removing points in this story can be important in some cases and not in others. So yeah, that'd be
that's the thing that confuses me. But
so yeah, maybe we should talk offline. Yeah. Great. Oh, and so with respect to these two definitions, one important feature about the way that I gave these definitions is that this x sub r, we can think of that as it contains the large n limit of the modular flow of operators in B sub r. So if I take this restriction to the subregion, I construct them, for finite n, I construct the modular operator with respect to the state psi and that subalgebra BR. Then if I do this modular flow, essentially by this JLMS criterion, we expect that those modular flow operators should survive the large n limit, and so in particular those operators are included in x sub r, and that fact can be important for cases when x sub r exceeds the corresponding y r hat. Great. So I'll just I'll sketch the procedure for how we go about identifying the bulk subregions that are dual to these large N algebras. I won't do the explicit computations as they're pretty messy, but I'll sketch the general procedure, and that's like this. So first we write down the global reconstruction of some bulk field, phi of x, in terms of generalized free field modes. So we do need as a starting point, in order to be able to talk about various operators being located at specific points in the bulk, we do need this notion of global reconstruction. And then we begin to work only on the boundary. So we compute the expansion of the generalized free field that should be dual to phi in terms of modes that are elements of this algebra for whatever subregion of interest that we're studying, and those of its commutant. And so those modes in the subalgebra and its commutant should be able to describe all of the possible operators in this GNS Hilbert space, and so we can give a mode decomposition of the generalized free field in terms of these sort of two sets of modes, of localized modes. And then we have two different expansions for the generalized free field, one in terms of these global modes and one in terms of these localized modes. And we can just compute a change of basis to go from those global generalized free field modes to the localized generalized free field modes. And then essentially we're done. We define the bulk subregion dual to the boundary algebra to be those locations x, those bulk points, at which the operator phi of x has no overlap with generalized free field modes in the commutant of the algebra that we're studying. So in particular, we had phi of x as a mode expansion in global reconstruction from this first step. And then we simply take those global modes and use this change of basis to write them in terms of localized modes. And for very special choices of x, the overlap with any of the modes that are supported in the commutant of the algebra will be 0. And for those special x, we say that they're included in the bulk dual of that algebra. And so in particular, this defines the bulk region via this boundary only procedure. It's just some change of basis on the boundary between different mode expansions. And interestingly, this RT surface emerges from these boundary algebras. So that's sort of the general procedure, and I'll give a couple examples where we can work this out explicitly. So I'll start with some examples related to subregion-subregion duality. In all these examples, I'll draw a time slice of Poincare ADS. So for example, if we take a half space, so if we imagine this is a time zero slice of Poincare ADS, if we take some half space, x greater than 0, then in that case, the bulk dual is just this region, where I extend to finite z, finite radial coordinate in the bulk, but I still have to have positive values of that x. And in this case, it's actually the case that this x algebra and the y algebra coincide. And this is hopefully not surprising. We know that in this half space case, the modular flow, the modular flow is just some geometric transformation, and so you sort of don't get any extra algebras by doing the large n limit in these two different ways. Another example, which is conformally related to the previous example, is the case of an interval where we just have some finite interval here in blue on the boundary, and the bulk dual is just the region that's shaded here inside this semicircle, and in that case, again the modular flow is just geometric, and these two algebras coincide. And so in both of these cases, we expect the entanglement wedge and the causal wedge to coincide, and indeed those algebras, those local algebras do coincide. So for a more interesting example, consider the case of separated half spaces. So here I'm using S to denote some sort of left half space that goes off to minus infinity, and R to denote some right half space that goes off to plus infinity in this direction. But I instead of taking them to be complements of each other, I put some finite separation in between them. And what we find in this case is that the bulk dual, or the bulk dual of this algebra y that's obtained additively, this y of r hat union s hat, that bulk dual is just the causal wedge. So we have to have x less than some critical value and x greater than some critical value, but that's sort of it. Whereas if we go through the other construction, where we sort of we include the modular flow for these operators for this joint algebra between S and R, and then take the large n limit, we actually get this whole shaded subregion here that's exterior to this semicircle. And so this is an example where the entanglement wedge exceeds the causal wedge, and in particular this algebra, this X algebra that's associated to that subregion exceeds this other natural algebra Y that could also be associated to that subregion. And so this is the general story for subregion-subregion duality. But as I mentioned, subalgebra-subregion duality also allows us to study some more general bulk subregions. So in subregion-subregion duality, we always need to be studying these bulk subregions that are bounded by some boundary anchored extremal surface. There should be the word bounded here. Sorry. And those are the types of bulk subregions that we can describe in subregion-subregion duality. But in subalgebra subregion duality, we can actually describe more general bulk subregions. And sort of the way that this works is that that in this large n limit, even for non-causally complete boundary spacetime subregions, which I'll denote by R now. So now this is some spacetime subregion that does not need to be causally complete. We can actually still assign the algebra M sub R. We can take the generalized free fields and restrict it to that subregion and take the double commutant. And these are exactly the algebras that I said should be dual to the causal wedge of R. And so now I should be careful that when I define the causal wedge of R, I don't first take the boundary causal completion. I just take R as a boundary spacetime subregion and consider the causal wedge of that. And so a very interesting case of this are so-called time-band subalgebras. So here, what I've drawn is some I'll denote by capital T, some time band on the boundary. So here, if I imagine, that the boundary is a circle, and then I have Lorentzian time running up in this direction. What a time band is here is that I take the whole boundary spatial slice, but I restrict the time to be within some finite interval here. And in particular, this M of t can be a non-trivial subalgebra. It's not necessarily just equal to the full M sub psi, the full algebra of single trace operators. So I can define these subalgebras related to non-causally complete bulk subregions. And in particular, since these algebras M sub r that I obtain in this way are additive, we can build up this algebra for any R, not just a time band like this, for any space-time subregion, by combining the algebras of all these small diamond-shaped subregions that fit into that space-time subregion and whose union covers that space-time subregion. And so why is that an interesting thing to do? Well, that's because in many cases we understand the bulk dual of these for these diamond-shaped regions, whereas we might not understand it for more general regions. And this allows us to deduce the bulk dual of this kind of time band algebra. And in particular, for one of these time band algebras, on a particular Cauchy slice, so in this example here, it would be a slice on the time reflection symmetry axis of this time band. On that particular Cauchy slice, this time band algebra includes all of the operators that are near the boundary. And so I should mention this procedure of building up these algebras from these small diamond subregions is very similar to an approach that was used many years ago to study the duality of the area of general bulk surfaces with what's called differential entropy in these papers. So I'll give now a couple of examples where we can understand the dual of these time band algebras very explicitly. So first, let me remind you. Oh yes. Yeah.
Are you going to comment on this differential entropy, whether you can obtain the value of differential entropy by somehow cross-producting this time band algebra with something? Do you have any?
Yeah. So I don't really have anything to say about that. I think it's a very interesting question if we can use those kind of cross-product constructions to give this well-defined notion of entropy and then relate it to the differential entropy.
It seems like the natural generalization of the black hole entropy. That would be the next step, right?
Yes, yeah, for sure. That would be the next step.
Okay, thank you.
But yeah, I don't have any concrete comments to make about that. Yeah. Great. Okay, so let me remind you that in vacuum ADS. So here I've just we imagine identifying these lines here on the left, so that wraps up into a cylinder on the boundary. If I consider the dual of some diamond-shaped region like this, then it's well known that the causal wedge of that, if I take its intersection with a bulk time slice, so now here I'm drawing a time slice on this time reflection symmetry axis of the diamond, I get some subregion that looks like this shaded region here. And so now that's the story for a causally complete subregion, and this is a case that can also be described by subregion-subregion duality. But now what I can do is I can take the additive algebra, where I just take many of those diamonds and I take their union, and of course in the limit that I union over the centers of those diamonds, scanning over the entire boundary angle, I will get exactly a time band here on the boundary. And the bulk dual of that, its intersection with the time slice looks like this. So it's this whole blue region here. So this here is shown for the case that I take some discrete union of 16 of those diamonds, but in the continuum limit, where I take sort of the union over all possible centers of those diamonds on this slice, then this draws out the exterior of some circle in the bulk. And another example we can study is in the case of BTZ. So again, if I consider some boundary diamond subregion, then on the time symmetry slice in the bulk, I get some subregion that looks like this. That's outside of the black hole. In particular, this will never get near the black hole because I'm building these algebras. I'm building these algebras out of this additive net that's dual to the causal wedge and not the entanglement wedge. So we don't see that phase transition in this case. And so again, if I take this union of diamonds so that I can form the time band, so that I cover this time band on the boundary, in the limit that I take a continuum of those diamonds unioned over all the centers, I'll end up with this algebra that on a bulk time slice is the region exterior to this circle. It's this blue region here. Right. And sort of we can also draw this on the Penrose diagram. Now that we have the spherically symmetric subregion, we can draw this on the Penrose diagram, and so the causal completion of that blue region I showed here on this time slice, the causal completion is some subregion that looks like this. It's some wedge region that reaches into the bulk. And in particular, this subregion here that's dual to this time band algebra is not a kind of subregion that can be described only by subregion-subregion duality. And so in particular, we can now study what I'll call deep bulk subregions. These are bulk subregions with no points near the boundary. And so how do we describe that? Well, we saw that if we took a time band, then on a particular Cauchy slice, we would get we would describe all of the near boundary points on that Cauchy slice. And if the bulk free field theory obeys duality as we expect that it should, then the algebra of the complementary region can be identified as the commutant of that time band algebra. And so one important thing to note about this is that if we tried to find some finite n analog for m sub r, we would just get the full boundary algebra because we cover a Cauchy slice, and we would have a trivial commutant. And so in particular, these bulk regions that have no points near the boundary, they seem to be sort of entirely emergent. They only emerge in this large n limit, and there doesn't seem to be any sense in which we can understand those subregions at finite n. So I'll just give an example, which is essentially the commutant of an example I already gave. So in vacuum ADS, we're looking at the t equals 0 slice. Remember that the time band algebra was this sort of annulus region out here, and the commutant algebra should then describe this region only here in this red disk, just of operators near the center of ADS. Great. And so now I'll just give a very quick discussion of the connection to quantum error correction. So subregion duality was very fruitfully understood in the language of quantum error correction. But in particular, something that you need in that discussion is to embed this bulk Hilbert space in the boundary CFT Hilbert space. And that's sort of the basis of those constructions. And in fact, what we find is that embedding in this G Newton goes to 0 limit, or the n goes to infinity limit, that embedding should not exist. And that's because the semi-classical bulk physics is dual to this GNS Hilbert space, which is actually not a subspace of the CFT Hilbert space, because the full CFT Hilbert space does not survive the large n limit. But what's still interesting about this is we can sort of understand why does quantum error correction work so well. And I think this is related to the delocalization of quantum information. And in particular, these holographic quantum error correcting codes they're codes in which information is delocalized on the boundary, and that's how they can correct for erasures. And I think this is intimately related to these violations of additivity that one finds when we take the large n limit. And so this is sort of a more speculative statement, but I think it's something that's interesting to explore. And so coming back to this general slide about the ADS-CFT correspondence and its semi-classical limit, we've now understood that these space-time subregions in the bulk should be described in general by these emergent type 3.1 algebras that come out of the large n limit of the CFT. And then I didn't talk about it in the talk today, but we can also understand event horizons as being related to the properties of those type 3.1 of those type 3.1 algebras, and we can also understand those infalling times in terms of this special property that's possible for type 3.1 algebras called half-sided modular inclusion. And so I'll just conclude with some future directions. So one thing is we'd like to understand better the emergence of these type 3.1 algebras in specific models in the large n limit. So as Nima mentioned earlier, one I think really interesting area to study this is in the SYK model, where we expect to be describing ADS2, and we should see this type 3.1 algebra emerge. It would be very interesting to study it in that very concrete setting. We'd like to understand the roles of these bulk singularities and how they're resolved in the boundary theory. As I mentioned, we can understand a bit about the emergence of these interior regions, these regions with no points near the boundary, and I think we understand that fairly well in the case of a two-sided black hole. But we'd like to understand that in the emergence of the black hole interior for single-sided black holes, as was discussed a couple times. We'd like to understand the physical implications of these type 2 algebras that we can get by doing the cross product. We'd like to understand how these are related to cosmological spacetimes, and also the more general these notions of entropy that can be associated to general bulk surfaces. It would be really interesting to understand how this algebraic approach and the fact that we now can understand some algebras that are dual to those more general bulk subregions. How would we go about understanding a notion of entropy for those algebras, and does this compute some area in the bulk theory? And so thanks very much for your attention, and let me know if there are more questions.
Thank you so much for the great talk. Are there questions?
Yes.
No, go ahead, Martin.
No, just another question. I think in all this, you are assuming that the ADS-CFT is correct, but are you checking somehow, for example, the duality or things like that with this?
Right. So, I would say that I think this is in a sense trying to understand. So trying to understand what the what ADS-CFT duality looks like at what ADS-CFT duality looks like in this semi-classical limit. So I think, for example, in this thermal field double example, if ADS-CFT duality tells us that we should be able to describe some sort of eternal black hole, then the sort of local bulk field theory that we get in the semi-classical limit, that has to be those local algebras have to be type 3.1 algebras. And so what this means is that if ADS-CFT duality is correct, it has to be able to produce these type 3.1 algebras in the same limit, which corresponds to the n goes to infinity limit. So I think there's a sense in which this can be viewed as a sort of check of the ADS-CFT duality in this semi-classical limit.
Okay.
So I think there's a sense in which this can be viewed as a sort of check of the ADS-CFT duality in this semi-classical limit. So I think there's a sense in which this can be viewed as a sort of check of the ADS-CFT duality in this semi-classical limit.
Thank you.
Sorry, I'm gonna continue on Martin's question actually. So it seems tempting to make the following statement. So you identify these type 3-1 algebras in large and limit. Then that's not holography yet. We usually assume some sort of large gap assumption, right? So here you're saying that the analog of the large gap assumption is the phase transition at black hole formation phase transition at beta, right? A standard ON model will not undergo such phase transition, right? So that is also associated with the formation of these type 3-1 algebras. Is that how you would summarize it, or how would you say, what's the role of the large gap in this story?
Right. Right. Yeah. That's a good question. So I think So I think what will not happen sort of exactly as you mentioned, in these non-holographic cases, we shouldn't see something like the Hawking-Page transition when we go and try to construct these large N algebras. So the particular dynamics of the theory is important, and in particular that's important because these sort of large N these large N algebras are essentially these theory. It's essentially a theory of the correlation functions of single trace operators, and so those and in particular you need to know those single trace operators. You need to know that those like those 2-point functions at all different values of the time separation. And so the actual dynamics of the theory gets encoded in the behavior of those 2-point functions, and that in turn affects the type of algebra that you get in the large N limit.
Yeah, but the thing that confuses me is this story of the time band. That sort of time band does not assume anything. To me, it seems like it's completely independent of this large gap story. Is that correct?
Right. So I guess right. So okay. So sorry. So
you draw this annulus, the bulk.
Right.
You say that the algebra of the operators outside of, in this annulus, outside of the central region, closer deep, sorry, not deep, closer to the boundary, is related to the type 3-1 algebra that you associate with this time interval on the boundary, right? So far, you don't need to invoke any large gap, strong interaction, strong coupling assumption, right?
Right. I mean, I think that those right. So those right. So those kind of I think right those kind of effects like strong coupling and the large gap will have an effect on these correlation functions of the single trace operators.
But then you identify a subalgebra that's type 3-1, right? You just say that this is the algebra that you get by multiplying single trace operators, where the number of multiplication is not allowed to scale with n.
Right. And so right. So I think maybe one maybe I think one thing that I didn't discuss is that in that case, if you take sort of a sufficiently large time band on the boundary, you should again collapse to this sort of full single trace algebra. And so this is sort of reflected in the fact that Maybe that doesn't answer your question, though.
Yeah, we'll
yeah.
discuss that offline. It's all right. I
Yeah,
will
yeah.
let other people ask questions.
Yeah.
Any other questions for Sam?
I have one question. So Sam, consider the bulk region which is outside the causal wedge but inside the entanglement wedge.
Mhm.
And if I look at the algebra of that, is there a like boundary dual of that?
So you mean, sorry, the algebra only in this sort of extra region. Yeah.
Right.
Right. Right. So right. I guess so. This should be some sort of purely yeah, this will be some sort of purely bulk subregion that won't have any near boundary points, because the near boundary points for the entanglement wedge and the causal wedge will coincide. And so right, and so in that case, I would expect that I should be able to define it in terms of the commutant of some particular time band, but I'll have to wiggle the time band up and down to completely describe the exterior of that surface. Does that answer your question?
Yes. In some sense, like boundary of entanglement wedge and causal wedge are the same. It's like they are anchored in the same point on the boundary.
Right.
Right. So your bulk region of interest also goes all the way to the boundary in some sense.
Right. So both the entanglement wedge and the causal wedge contain points that go all the way out to the boundary. But in this case, the points that are outside of the entanglement wedge but inside the causal wedge, oh sorry, the other way around, that are outside of the causal wedge and inside the entanglement wedge, those points are not near the boundary. Because the causal wedge and the entanglement wedge asymptote to the same. They asymptote to be the same near the boundary.
Right. Okay.
Yeah.
Sorry, this is precisely the reason I was asking a question about inclusion of type 3.1 inside type 3.1, because it's tempting to identify these operators, this region outside of the causal wedge, but inside the entanglement wedge, as the relative commutant of this inclusion. Right? So, but then the question becomes, is the relative commutant type 3.1? What is the relative commutant? And I think it's much easier to address this question in the case that one of the algebras is type 1, in which case we do know the relative commutant is type 3.1.
Ah, okay, yeah, that's very interesting. Yeah.
Yeah, anyway, that's the reason I was asking the question.
Right. Oh, okay, yeah, very interesting.
Yeah. All right, any other questions? Any last questions for Sam? If not, let's thank Sam once again for the great talk. And we hope to see you in person sometime soon.
Yeah, that would be great. Yeah.
Thanks for the great talk.
Yeah, thanks so much for the invitation.
All right, thanks everyone.
Okay.
Have a nice afternoon. Bye.
Yeah.